Okay, today we're going to continue our talk on atoms and elements. So we already talked about the periodic table some, but let's talk about groups. So a group is a vertical column of elements that have similar properties. There's two big groups, the main group elements and then the transition metals. So the main group elements are here, these two columns, and then this part of the periodic table over here. So basically anything with an A after it in the group is main groups. The transition metals are here in the center. And so those are the two big groups that we divide them into. And then each individual vertical column, though, is considered a group. So here are the alkali metals. Group 2 is the alkaline earth metals. Group 7A are the halogens, and group 8A are the noble gases. So let's talk about the alkali metals. These are group 1A, or just group 1 you'll see on some periodic tables. These are very reactive metals. They react vigorously with water. They're soft, shiny, good conductors of heat and electricity, and they have low melting points. So if you look here, here is sodium in water. So if you put sodium in water, it catches on fire. Then the alkaline earth metals, group 2A or group 2, they're fairly reactive, but they're not quite as reactive as the alkali metals. So if you look here, here's calcium in water. So you can see it bubbles vigorously, but it doesn't have the fire like sodium does. And then the halogens are group 7A or 17. These are very reactive nonmetals. Chlorine is used as a sterilizing and disinfecting agent. We use iodine, I2, to do kinetics reactions, so we can actually watch the rate of reactions, use some reactions using iodine. We use bromine a lot in organic synthesis, but yes, these are very, very reactive as well. And then the noble gases, group 8A or group 18, these are really unreactive gases. And we'll talk more about why some groups are really reactive and some are really unreactive. Okay, let's talk about ions. So an atom loses or gains electrons to form a charged particle called an ion. And the ion charge is equal to the number of protons minus the number of electrons. So for example, here we have lithium. Lithium will lose an electron to form lithium plus. We can calculate our ion charge this way. So it has 3 protons, lithium, and then it has 2 electrons, so 3 minus 2 is 1 positive. We get the 2 because the uncharged lithium has 3 electrons, but since we lose 1 electron, now we're at 2. Then if you look at fluorine, fluorine gains an electron to form F minus. So its ion charge is -1. It has 9 protons, and fluorine normally has 9 protons in the uncharged species, but electrons, but we gained an electron, so we have 9 minus 10 equals -1. Here's ions in the periodic table. So group 1 tends to form +1 ions. Group 2 tends to form +2 ions. Group 7 tends to form -1 ions. And group 17 or 7A, -1 ions. Group 6A or 16, -2 ions. And those are the predictable groups. And then nitrogen tends to form a -3 ion. And then aluminum, Ga, and In tend to form +3 ions. So those are all the ones that we can predict and the ones that you should know. And then also just know transition metals form cations with various charges. And we'll talk a little bit about that later. Okay, let's talk about the mass number. So the atomic number is the number of protons in an atom, but the mass number is the total number of protons and neutrons in an atom's nucleus. The mass number is equal to the number of protons plus the number of neutrons. And the number of neutrons then is equal to the mass number minus the atomic number, because remember the atomic number is equal to the number of protons in an element. Okay, let's do some practice. So zinc has a mass number of 68. Determine the number of protons, neutrons, and electrons. So our atomic number equals 30, which is 30 protons. We get that from the periodic table. The mass number minus the atomic number is equal to the number of neutrons. So we're told our mass number is 68. We subtract the atomic number, which is the number of protons, and we get 38 neutrons. And then the electron should equal the number of protons in a neutral atom, so we should have 30 electrons. Isotopes are atoms of the same element that have the same atomic number but a different number of neutrons. So what does that mean about the mass number for the isotopes of the same element? It will be different, right? Every isotope of a particular element will have a different mass number because the mass number is the number of protons and the number of neutrons. The number of neutrons is changing, but remember the number of protons does not change because that defines an element. So every isotope will have the same atomic number, the same number of protons, but a different mass number, which is the protons plus the neutrons. And we'll often write isotopes like this here in this AZX format, where A is the mass number, Z is the atomic number, and X is the chemical symbol. You'll also see it without the Z, and you'll just see the A and X sometimes because Z never changes for that particular element, so we don't have to write it there. Okay, so let's look at magnesium. So you can see here magnesium has an atomic number of 12, and this particular isotope has a mass number of 24. So if we go down here, what we call this isotope is magnesium 24. So we say the name of the element and then the mass number. And we can write it like this, Mg-24. So number of protons in magnesium is 12. It's a neutral element, so the number of electrons are 12. The mass number is 24, which we get from up here, or the name. So our number of neutrons should also be 12, 24 minus 12. And this is its percent abundance. This means 78.70% of magnesiums in the world are magnesium 24. And then here's two other isotopes of magnesium. We have magnesium 25 and magnesium 26. So again, all these isotopes have the same number of protons, 12, which we get from the atomic number. They all have the same number of electrons because they're all neutral atoms. What's different is the mass number. We have 24, 25, and 26. And that means the number of neutrons is different. So magnesium 24 we have 12, and magnesium 25 we have 13, and magnesium 26 we have 14. And again, we get that by subtracting the mass number by the atomic number. And then the percent abundances, so for magnesium 25 we have 10.13%, and magnesium 26 11.17%. You'll never have to figure out the percent abundance. That's something that's determined experimentally, and that will be given to you. Okay, so let's talk about atomic mass. It's directly below the element symbol on the periodic table, and this is the average atomic mass. So if you took a sample of all the magnesiums, what's the average atomic mass? And we can't just add up the mass numbers or the masses of the different isotopes divided by the number of isotopes, because remember here we talked about how they have different percent abundances. So if I just added the mass of magnesium 24, magnesium 25, and magnesium 26 and divided by 3, I would be assuming that each isotope has an equal abundance, but that's not the case. So to calculate the average atomic mass, that's equal to the fraction of isotope 1, or its abundance, times the mass of isotope 1, plus the fraction of isotope 2 times the mass of that isotope, plus the fraction of isotope 3 times the mass of isotope 3. We just get the fraction of each isotope by taking the percent and dividing by 100. So the fraction for magnesium 24 would be 0.7870. For magnesium 25, it's 0.1013. 26, it's 0.1117. So let's look at an example, or let me show you some average atomic masses versus the isotopes. So you can see here lithium has two isotopes, 6 and 7. Its average atomic mass is 6.941 AMU. Its most abundant isotope is lithium 7. We can determine that just by looking at the average atomic mass, because the average atomic mass is closest to 7, which is its mass number. So whatever isotope the average atomic mass is closest to will be its most abundant isotope. So if we look at carbon, carbon has 3 isotopes, 12, 13, and 14. Its average atomic mass is 12.01, so its most abundant isotope is carbon-12, so on and so forth. So here's just another visual representation of the isotopes of magnesium. So here it's just showing again the vast majority of magnesium atoms are magnesium-24. Okay, again, like I said, the average atomic mass is the average mass for each element. So let's look at a couple examples. Here we have chlorine. So chlorine has 2 isotopes, 35 and 37. Chlorine 35's isotope is the abundance of chlorine 35 is 75.77%, and its atomic mass is 34.97. Chlorine 37's abundance is 24.23%, and its atomic mass is 36.97. So to calculate the average atomic mass, remember we multiply the fraction of isotope 1, which is chlorine 35, and that's fraction is 0.7577, and we multiply it by chlorine 35's mass. Then we add that to chlorine 37's fraction, 0.2423, and we multiply that by its atomic mass, 36.97, and we get 35.45 for chlorine's average atomic mass. And you can compare that to the periodic table. It should be the same as what's on the periodic table. Let's look at another example. Gallium has 2 isotopes, gallium-69 with a mass of 68.9256 AMU and a natural abundance of 60.11%. And gallium-71 with a mass of 70.9247 AMU and a natural abundance of 39.89%. So calculate the atomic mass of gallium. Well, again, its atomic mass will be equal to the fraction of isotope 1, which is 0.6011, times the mass of that isotope, 68.9256 AMU, plus the fraction of isotope 2, 0.3989, times the mass of that isotope, 70.9247 AMU. So then we get the atomic mass is equal to 41.4312 AMU, that's from here, plus 28.2919 AMU, that's from this part, and we get 69.7231 AMU. You shouldn't ever have to do an average atomic mass calculation with more than 3 isotopes. I won't give you one that has more than 3 isotopes. It doesn't get any harder the more isotopes you have. It just takes a long time, and I can gauge whether or not you understand this with elements that have 2 or 3 isotopes. You don't need to show me that you can do 6 isotopes. If you can do 2, you can do 6.